So thanks everybody for making time in your calendars and coming to listen to the talk which I'm going to present. It's entitled Constraining European Fossil Fuel Emissions using the ICOS radiocarbon observations. And this work was mainly conducted by Maxim Garkivsky, a PhD student who worked in our laboratory and finished last autumn. And he worked under the supervision of us and together with Christian Rödenbeck and Christoph Gerbig from Max Planck Institute in Jena, who provided us with the modeling tools and the modeling expertise which we needed in order to perform this study of our ICOS observations in an inverse modeling setup. So when we are talking about ICOS observations, ICOS radiocarbon observations are conducted at a subset of the ICOS atmosphere stations. These are the ICOS class 1 stations, which perform the radiocarbon observations. And they are going from Zeppelin in Svalbard down to Lampedusa in the Mediterranean. And it's basically one stripe of stations from Scandinavia over Central Europe. And now, since 2025, we also have the Italian stations, which we are welcoming in the ICOS network, which unfortunately have not been part of that study because they just joined very recently. An ICOS station is typically on the continent a tall tower with 100 to 200 meters, and the C14 is always collected on the topmost level. So the outline of the talk today is that I want to roughly introduce you to radiocarbon in the atmosphere before I show you a way how we can use atmospheric radiocarbon observations to deduce the offset of fossil fuel concentrations at the measurement sites. And then we'll enter a part where we use the model to investigate how much information content is embedded in those ICOS observations and what can we retrieve in the best case of an idealized model world from those data in terms of fossil fuel emission verification. And in the last step, we really use the actual radiocarbon observations, look at the results, how well do they help us to constrain those emissions, and what are the limits. So let's come to radiocarbon in the Earth system. And radiocarbon is constantly produced naturally by cosmic rays, and those cosmic rays produce thermal neutrons, and this happens in the lower stratosphere and upper troposphere, and then these thermal neutrons are captured by nitrogen-14 and thereby forming carbon-14. That carbon-14 is quickly oxidized to 14CO2, and from here on it is labeled and takes part into the global carbon cycle, meaning it gets photosynthesized by plants and then finds its way into humans via eating those plants, and it gets dissolved in the oceans, forming then also carbonates and bicarbonates. When I show you radiocarbon observations in this talk, they will always be in the unit of capital delta 14C, which for today's talk, it's sufficient for you to know that this is a ratio of the C14 atoms to the total carbon atoms in that sample. And the natural equilibrium between C14 and C12 is 10 to the power of minus 12, which is very little. And we are measuring that quantity down to the precision of a couple of per mil. So if you want to put that into perspective, it is like if you want to measure the distance between Sun and Earth, and you want to do that down to the millimeter scale. It's radioactive and it has a beta decay, and it decays with a half-life time of 5,700 years. So mankind, which is depicted here as cavemen, they altered the radiocarbon in the atmosphere, and we did that by the burning of fossil fuels, which are millions of years old since they formed. So they once contained radiocarbon, but this has all long been completely decayed, and when you now burn a fossil fuel, you release 12 CO2 to the atmosphere and smaller amounts of 13 CO2, but no C14 anymore. And this is depicted in this graph, which we are seeing here on the right-hand side, which is spanning from 1860 to recent times. And in the topmost part, we have CO2. And in the middle part, we have the anthropogenic CO2 emissions, and you see they were rising, and as a consequence, the CO2 concentration in the atmosphere rises as well, which is here retrieved from Antarctic ice cores. If we now look at C14 on the other side, the C14 value given in those capital delta 14C unit is decreasing, because this is a unit which gives you, again, the C14 content, which stays unchanged if you burn fossil fuel CO2, because this increases the total amount of carbon while letting the C14 unchanged. So it lowers the C4 delta, capital delta C14 value in the atmosphere when we burn fossil fuels. And this effect is called the Suess effect, named after Hans Suess, who published that effect first in 1955. This is not the only change mankind put on the radiocarbon cycle. From 1945 on until the partial test ban treaty in 1963, there were many tests of nuclear bombs in the atmosphere, and they produce thermal neutrons in the same region, so in the lower stratosphere, upper troposphere, as the natural production mechanism as well. And therefore, we produce a bomb radiocarbon signal, which then gets also oxidized and takes part in the carbon cycle. And this is this huge peak, which you cannot even see in this record, but you can see it on this next graph, where you see the entire tropospheric 14CO2 activity from the 1914s to today. And you saw that just right before the test ban treaty came into place, many nations did their last tests of nuclear bombs, and that made this pronounced spike in the atmosphere, which was then used by Ingeborg Levin and her co-workers and others to really investigate now the dynamics, how this C14 signal is transported from the atmosphere to the biosphere and the ocean. And from here, you can really learn something about the exchange times in the carbon cycle. And I refer you to this paper of Ingeborg Levin if you want to see how these radiocarbon data can be used for this purpose. Today, we will use the Suess effect. We will use the dilution of the atmospheric C14 to C ratio by the 14-free emission of fossil fuels. And we do this by applying the so-called Regional Isotope Budget Approach, which I will explain very briefly now. And those of you who have seen talks from our group before are very familiar with this sketch, which is originally made by Ute Carstens and which we keep showing since 20 years. But it depicts very easily the principle of the Regional Isotope Approach. So what are we looking at? We are observing the ratio of C14 atoms to C12 atoms in a clean background air sample. And we're comparing this to the C14 to C12 ratio of a sample which is taken closer to the regions where we have fossil fuel combustions. And those fossil fuel combustions increase the C12 amount by letting the C14 amount unchanged. So this lowering of the C14 to C12 ratio in the vicinity of the fossil fuel sources is a direct measure of the additional quantity of fossil fuels which have been emitted into the atmosphere. In reality, things are not always that easy. Also for C14, we are having effects which we need to consider, and this is the nuclear discharge of C14 from the nuclear industry, which is mainly power plants and reprocessing plants, and they produce C14, but they don't produce C12. So what we need to do is we need to get the emission data which are officially reported from the nuclear industry, and then we account for them in our observations and correct for them as good as we can. So how does this regional isotope budget approach work in practice? This is the map of the ICOS atmosphere class 1 stations. And since we are in Europe, we are living in a west wind drift zone. So meaning most of the time we have marine air masses coming from the Atlantic and then traveling over our European continent and over the sites. And luckily, in addition to those class 1 sites, we also have radiocarbon observations at Macehead, which are only sampled when the air masses are coming from a marine sector. And from these samples, we deduce a background for Europe for those Atlantic air masses. Maya et al., in this paper, which is listed at the bottom, they investigated how well is this assumption that in Europe, Macehead is really a proper boundary or a proper background station for these observations in Europe. And what they did is they calculated back trajectories for a couple of ICOS stations, 10-day back trajectories, and they looked where do those trajectories leave this European domain. And what you're seeing is the probability of those back trajectories where they leave the domain on the outer parts of that sketch. And what you see is that in 2/3 of the time, the trajectories really leave the European domain via the western boundary. And the probability is highest between 50 and 55 degrees north, actually making Macehead a really proper place to estimate the background for this European station set. In 1/3 of the time, however, you have easterly winds, or you have sometimes in northerly winds, and in those cases, Macehead might not be the proper boundary condition for the European continent. And this is a problem which we will come back to afterwards in the last section of today's talk, when we talk about the limitations of the Regional Isotope Budget Approach. But first, let's take this Regional Isotope Budget Approach and look how large are the signals, how does it look like in reality. Therefore, I show you now the European C14 background as it is fitted to Macehead observations in green here, and we now compare those in the next steps to the observations which are performed at Lindenberg, which is an ICOS station in Germany. And these are the blue dots, individual flasks collected at Lindenberg. And the difference now between the background and the observations at Lindenberg is exactly this depletion due to the fossil fuels. And this can be translated into the additional enhancements of fossil fuel at Lindenberg sites. And what you're also seeing when you're looking at that graph is that there are two very different data frequencies. And the first data frequency here is the native radiocarbon analysis frequency, which we have in ICOS, and that is 1 flask every 2 weeks. In 2024, in a European project called CORSO and in a subsequent COMS project, we now changed this analysis frequency to the native flask sampling frequency. In ICOS, we sample a flask every 3rd day, and due to these two projects, we now had the chance to really analyze all of those flasks, which are sampled anyhow, for radiocarbon. And you see that there is a large difference in the availability of the data, of the radiocarbon data, which we're having. What you also can see is that during summer times, the fossil fuel concentrations are smaller than in winter. And this is very typical, and we see that for the entire network, which we can compare in these two following graphs. It's a European map, and what we plot on the z-axis is the fossil fuel enhancement in ppm, fossil fuel, for the individual ICOS stations with respect to the background in Macehead here. And what you are seeing is that dependent on the individual station and how much the individual station is in the footprint of larger fossil fuel emission regions, you have different fossil fuel enhancements. And stations here in Central Western Europe in winter, they reach fossil fuel enhancements between 4 and 7 ppm, while those stations who are more rural are only at an offset of maybe 3 ppm. And the Scandinavian stations, or Jungfraujoch here, they have very small signals between 0 and 1 ppm fossil fuels. This just reflects the surroundings of your stations and how much fossil fuel emissions you have at that station with respect to the background in Macehead. So this is the winter situation compare it to summer, then all of those fossil fuel enhancements are shrinking way down, which is due to the better vertical mixing in the atmosphere. So a larger dilution of the fossil fuel signals on top of the fact that in summer we have lower fossil fuel emissions in total. But what you are seeing is that since we have the same observational uncertainty, that our signal to noise ratio in winter is higher than it is in summer, and therefore in the later part of the talk we will often restrict ourselves to the winter time, because there we have more signal to noise ratio. So these are the data which we have at hand, and now we want to take them and discuss how much can we use those data to constrain the European fossil fuel emissions. And this is the next part. And if we talk about ICOS C14 data, there is actually more than one type of C14 data. What you're seeing here is the tower in Svartberget in Sweden, and we are taking samples from the topmost level. And if you look in the shed of Svartberget, then you see two different sampling devices which we use to obtain radiocarbon data. First is the ICOS flask sampler, and it collects whole air samples for 1 hour snapshots of the atmosphere. And the second device is the integrated sodium hydroxide sampler, which is continuously flushed over the course of 2 weeks with air from the highest level. So in this sample type, you have real integrated atmospheric conditions over 2 weeks. And we, as the central analytical laboratory in ICOS, we need to ask the question, which of those sample types are more valuable if you want to constrain European fossil fuel emissions? Are there differences? Which one should you go for? Because, as you have seen, we are limited in our capacities and also in the amount of funding which we have to perform those analyses. So therefore, we performed something which we called a synthetic information content assessment of the existing radiocarbon data, and our goal was to know, we have C14 data available, and how much can we learn from that data which we are actually having in an idealized model world about fossil fuel emissions. And we are doing that by using synthetic observations, but only at real sampling times and with realistic uncertainties. So you can think of it as a kind of an Aussie without changing the actual observation network, but more with the idea of how much can we constrain the emissions from the existing network. To those of you who are not so familiar with an Aussie concept, I quickly went through it. So what we are doing is we are starting with assumed to be true fossil fuel emission map over Europe. Here, this is the Global Carbon Project gridded version. And then we take a transport model, in our case it was STILT, to generate synthetic fossil fuel concentration enhancements over the continent. And these we sample and we perturb those samples with uncertainties, 1 ppm for transport uncertainty and 1.5 ppm for the observational uncertainty, which we obtain from our Regional Isotope Budget Approach. And these are now the observations which we feed into our inversion system and see how well can they retrieve the truth. And if you're working in an inversion system, you have observations, but you also have a prior, which you use at the same time. And since we wanted to learn about the information which is only in our data, we supplied our inversion system with a flat zero prior, which basically means there are no fossil fuel emissions in Europe at all. No temporal variability, no spatial variability, it's just zero, temporally and spatially. And these are the two information streams which we provide to our inversion system. And the inversion system was the Jena Carboscope system, which then produces from this information a posterior fossil fuel emission map. And in the next step, we compare the true prior fossil fuel emissions and the posterior fossil fuel emissions, which are in this case only informed from our observations. And We defined a quantity which we call the truth recovery rate, which compares pixel by pixel what was the true fossil fuel emission, what is the posterior fossil fuel emission, and then sees how well was the truth recovered by our inversion system. And we're doing that spatially for the entire map. So 100% means we have completely recovered the true fossil fuel emissions, and 0 means there is no change compared to the prior flux. And now we compare that for our two different sampling types. And in the left-hand picture, you see the results for the integrated samples, and on the right-hand side, you see the results for the flasks. And if you go a little bit backward and look only at these two graphs, then they look really similar. You have a region here in Central Western Europe where the truth recovery rate is somewhere between 80 and 100%. And this is the same for both sampling types. And in the outer regions, the truth recovery rate is 0. And this is not so surprising if you now look at the black dots and see where our observations are taken. And you see that basically we have a large truth recovery rate at those locations where we have observations. And for example, in Spain or in Eastern Europe, there are no observations, and consequently, there is no truth recovery rate there. So for the rest of our talk, I will talk a lot about this Central Western European domain of Central Western European region, which is given here by this black square, because we now see that this is the region where we have data and where we can expect our data to inform us on the fossil fuel emissions. This is the network, how it was in 2022, and also the truth recovery rate for this year. That was not always the same since the beginning of ICOS. When we looked at the temporal development of the stations within the Central Western European domain, then we see when it started off in 2015, not all of the stations have been there, and they have been slowly coming over the development of the network, and in 2020 we reached the full coverage of the stations in this Central Western European domain. And now let's see what is the effect on the temporal change of the truth recovery rate. So we have now truth recovery rate on the y-axis, time on the x-axis, and we are looking at the development of the truth recovery rate. And what you are seeing is there are these steps which are equivalent to the extension of the network. And what you are seeing is at the same time, in the bottom part here, you see the monthly data availability of C14 in the network. And you're seeing that it is not changing quite much with the arrival of new station, which is due to the fact that for this type of samples, the integrated samples, we have a limited laboratory capacity and throughput. So if we have more samples, we distribute them among the stations, but overall, the amount of samples stays the same. But although the amount of samples stays the same, a better spatial coverage gives you a better truth recovery rate. So from this, we take the conclusion that spatial coverage is actually more important than a higher frequency of samples. This is what we learned from the synthetic studies of our ICOS observations, and now we want to use the real measured results and go with them into inversions and see how well can we retrieve or validate the fossil fuel emissions in that region. So again, we do a sensitivity experiment first to build trust in our data and to see how much information is contained only in the data. Again, we are doing an experiment with a flat 0 prior, so we assume no prior knowledge. We are only looking at the Central Western European domain, and we are now comparing the fossil fuel flux for this square, so for this domain. And to guide your eye and to give you an expectation of what bottom-up emissions for this region would say. The GCP, so the Global Carbon Project emissions, are plotted here in gray. And now let's invert the integrated samples which we are having. And that is the posterior emissions are now given in blue. And what you see is that they pretty much capture the seasonal cycle. So we have larger emissions in winter, smaller emissions during summer. The absolute value of our posterior fluxes are realistic. Let's say they are plus minus 10%, close to that what the bottom-up emissions say. And on top of that, they seem to independently confirm the trend which we are having. Yeah? So in blue, you see the downward trend, which you see at the same time in the GCP bottom-up inventory for that same period. That was the integrated samples. Let's look how the flask performs. So the flask, they start later. So from 2022 onward, we are starting to get some decent coverage for the flask, which is given here in the lower part. And you are seeing that these flasks are providing the same information of the seasonality and the absolute value and the trend, although those flasks are pointing to smaller fossil fuel emissions in summer because the prior is also pulling them low because the prior says there are no fossil fuel emissions. So that is a result which was really remarkable for us because we are only providing those observations which are or only the information which are in the observations and nothing from outside. Okay, this is not how you would do a proper Bayesian inversion, because in a proper Bayesian inversion, you want to make use of the information which is contained in your prior, and you want to improve it by the information which is contained in your observations. And therefore, in the next step, we took the GCP prior, we reduced the uncertainty to 4% prior uncertainty, because the fossil fuel emissions, especially in that Central Western European domain, are the well-known or the most well-known component of the carbon cycle. So we have very good prior knowledge, and therefore we only expect them to be wrong by only a couple of percent. But now let's see what happens if we run the inversion with this prior and our integrated samples. And what you're seeing is that the posterior wants to pull the GCP prior downward a little bit. You see it here in 2019, you see it in 2020, 21, which was the COVID period, but you again see it in 2023. So we want to come to lower emissions. If we compare them to the flasks, then the flasks, interestingly, don't see this deviation in 2023, and they stay really close to the prior emissions from the GCP. So I told you before that we have a larger signal-to-noise ratio in winter. So if we now want to quantify these changes, we restrict ourselves to the winter half, or not half, but the winter from November to February, and put those into numbers. So the black bars down here are giving the prior, and the posterior is given in the individual colors. And you are seeing a posterior change relative to the prior, which is for the integrated sample somewhere between 2 and 6% of the winter mean, apart from that year in 2023 where we have a larger deviation. And this is what we expect. Yeah, we would not expect that there are larger deviations than a few percent only, because as I said, these emissions are well known. For the flask, the deviations are even smaller, only between 1 and 5% of the winter fossil fuel emissions. So what we can say is that the posterior and the bottom-up estimates agree very well within a few percent. And the question is now, can we then use these observations which we're having to identify potential biases in the priors? Yeah, and that was the next example which we investigated. We officially biased our prior. So this is the GCP original, and then let's say we lower it by 10%. So where do the inversions with our data, where do they put the posterior now? And what we were really glad to see is that now the data is pulling it back upward and trying to really come back to the original fossil fuel emissions for the Central Western Europe. And the flasks do that even more. They even want to push it back up to that dotted line, which was the original GCP prior. And you can do that also with a plus 10% example, and the combined results are shown here. So in black dotted, you have the GCP, the shading is the plus minus 10%, and then in blue solid line, you have the posterior, and its shading gives you the variability of the posterior. Same for the flasks. And what you are seeing is that the shading from the prior is largely reduced when we compare it to the shading of the posteriors. And again, if we put numbers to that for the winter times, we are seeing that this prior spread of 10% is reduced to a posterior spread of 4% for the integrated samples and something between 2 and 4% for the flasks. So this shows you that the data is really offering us a potential that we can validate fossil fuel emission biases and retrieve them and correct for them. You might now say, okay, 10% prior bias is very unlikely because we know this component so well. This result holds true for many different prior spreads. So we tested it for 5% prior biases, 2%. And what you get very consistently is that the data reduces that bias by either 60% or 70%, depending on the sample type you choose. And this amount of reduction is then basically dependent on the prior uncertainty, which we assume. And in our case, we always had a prior uncertainty in this experiment of 4%. So these are great results, which we have. And I told you that we need to talk about some limitations of our effect as well. And that is how sensitive is our regional isotope budget approach to background biases in radiocarbon, which we are having. And therefore, we did other experiments, and we assumed that we have a bias in our background radiocarbon observations of 0.5 per mil. At that point, it's important that we distinguish uncertainties and a bias. For each of our background radiocarbon values, we assume that our fit has an uncertainty of 2 per mil, because there is variability around that. But what we are now investigating is there really a true bias? So are we forced in one or the other direction systematically due to wrong assumptions? And what we think also from the comparison of our background site at Macehead to the Nijverd Ridge or to Jungfraujoch or to other European background sites is that maybe 0.5 per mil bias is realistic, not so much more. Okay, let's rerun our whole inversion set with different C14-based fossil fuel data, assuming that bias in the background. And what you're seeing is now that our absolute value is really dependent on this assumption of the background. And to put it even clearer here, we run a second case where we had a 2 per mil bias, which we believe is unrealistic. But what you are seeing is that clear effect of that bias in the background, which we are having on the absolute value of our posterior. The seasonality is not affected. The trend is not affected, but the absolute value is dependent on the bias in our background. And it is larger for the integrated samples as it is for the flasks. You see that the range for the flasks is smaller, which is explained by the fact that the single flasks have a larger fossil fuel difference between MACET and the station than the integrated sample. And therefore, if the signal is larger, you are lower dependent on a bias in the background. So coming back to the realistic case of 0.5 per mil, and if we put that into numbers again, then we would say from that dependency of a bias in our background, we are restricted to a ±4% variation in the absolute values of our emissions for that Central Western European domain, and 2 to 3% for the flasks. So this is again in the order of those differences which we have seen between the posteriors and the priors. So these differences do matter, and we need to take care about on them. Yeah, and what we are now seeing is that this background sensitivity limits the applicability of our regional isotope budget approach, and we have to overcome that by explicitly modeling radiocarbon within the inversion system, because then we would move away from the assumption that these observations in MACET really for all times retrieve our global or our European background signals. And the good news is that Christian Rödenberg has already implemented C14 in the Jena Carboscope system in the global part, and we are now planning to extend that from the global part to the regional part. So with that, I come to my conclusion, and I think we could have shown that there are some great achievements in the ICOS C14 data, and with this reminder of a graph, I really want to remind you that we can independently constrain fossil fuel emissions in Europe, trend, absolute values, seasonality. The information on all of those quantities is within the data which we are observing, and we can use those data to reduce potential biases in backgrounds, potential biases in the priors, and therefore use those observations as a validation tool for the data which we retrieve either from bottom-up studies or from other top-down studies. There are still challenges, yeah, and the challenge, as I've shown you, is the accurate knowledge of the European background. There we hope that we can soon make the step to move away from the regional isotope budget approach and from the assumption of MACET being a proper background for all times, and move to an explicit modeling of radiocarbon. But still with that, we will need to extend the European and the global background monitoring, but also because also the model is dependent on the backgrounds of the European domain, and we need to determine them precisely in order to really make use of the full information content which we have over the continents. The next challenge is that the spatial coverage is really key, yeah, and if we want to learn more about European fossil fuel emissions, then we have to extend our coverage, yeah, and just as a small outline, what you are looking at here is the integrated radiocarbon sampler volume or version 1, which was invented basically by Ingeborg Levin in her master studies in the late 1970s, and it in principle did not change so much. And we are now working on a second version of that, which has the capability of multiple samplings within one sampler, and the opportunity that you have an 8 months of autonomous operation of such a sampler. And we are hoping that with such an autonomous sampler, we are overcoming the limitations of having a lot of personnel present at those stations to change the samples. And then we might think of installing these new samplers at other stations. And what you're seeing here again is class 1 ICOS sites. These are class 2 ICOS sites. All of them have a tower. All of them have a Becquerel, which is measuring precisely CO2 and CO. They have spare lines, and we might be easily able to convince them to install such a new sampling device. And we might even talk to our colleagues from the ecosystem domain, which also partly have towers, where we might use one or the other and install one of those samplers. And that offers us in ICOS the opportunity that we can really expand our spatial coverage in Europe much further to what we currently have. And with that, I thank you for listening, and I'm open for your questions.
Thank you, Sam. Thank you for that very comprehensive presentation and for demystifying, to some extent, for some of us, the use of 14CO2 in constraining emissions. There are quite a lot of questions, and I think maybe we can start with, we can take a couple of them. Dominic, Bruno, would you like to ask the question? This is about the use of filtering. Is it needed or not?
Yeah. First of all, thanks, Sam. That was really a great talk. Very impressive. My questions was about the nuclear power plants, which can also produce some 14C in the CO2, and you didn't seem to have any issues with that. So I was wondering whether you applied some filtering of the data that you presented, and if filtering is needed, wouldn't that be an advantage of the flask compared to the integrated samples?
Yes, you are completely right. I mentioned them in the introduction. So what we do is we correct for the nuclear component. We do so by trying to get the best temporal resolutions of the nuclear emissions, which is not easy to get because the operators most of the time offer only quarterly or monthly emission estimates, and we are trying to downscale them to a higher temporal frequency using the operating conditions of the nuclear power plants. That works for one type of the reactors better than for the other type. And then we calculate this nuclear correction contribution for each of our samples individually, also in the model, and apply that correction. This is not perfect. It is causing a correction on the order of, depending on the station, which one you choose, between a couple of percent up to 15–20%. Yeah. And therefore, what we do is, especially with the flasks, we already, before we ship the sample to our central analytical laboratory, we estimate the probability of that sample of being contaminated by nuclear emissions. Therefore, we assume constant emissions of the nuclear reactors and calculate the footprints. And if this potential nuclear emission exceeds a certain threshold, then we skip that sample, don't even take it, resample it, and ship it at atmospheric conditions when we expect to have smaller nuclear emissions. And that helps, according to the model results, to lower our total dependency on the nuclear emissions. Still, we cannot really deal with very spiky and unknown C14 emissions from the reactors as long as they are not known to us. And yes, you have a very important point here, is that the flask samples are way less dependent on these than the integrated samples. The reason why we think that integrated samples still have a large potential to help us is that those integrated samples have the opportunity that they can be analyzed multiple times. And you have the same sample, but you can run it 4 times. If you do so, you will basically decrease your measurement uncertainty by a factor of 2, which is currently the largest limitations when you use radiocarbon. And we are really hitting this measurement capacity since ages, and it hasn't it has improved a little bit, but not dramatically. And integrated samples offer you a possibility that you only need more funds to analyze the sample more often, but then you get statistically a much better measurement precision. And that is something which we want to investigate in future, how well that would help us to really improve the entire use of radiocarbon. But
Thanks. I think there are also other questions. I don't want to take all the time. Thanks. It was very clear.
Thank you. Thank you, Sam. That was so. Next we have from Rainer. He is asking about why the truth recovery rate is poor in the north comparatively. And there is a, maybe I feel like this is kind of related by Patrick from EMPA. He asks, how would you expect to compare improvements between better temporal coverage versus spatial coverage?
Rainer, to your question, the fact is that the fossil fuel signal in those Scandinavian sites is so small that the uncertainties which we're having in our observations are really dominating it. So, and then there is no signal left really for the inversion to improve. Yeah, that is the reason why we are not improving in the north, although there are observations. Yeah. Actually, what we do is we use those observations still, and we use them to constrain European background signals. Yeah, so it's a duplication. If you look at those time series of the high Scandinavian stations, they are duplications of the Macehead time record. Yeah. And the other question was about temporal and spatial frequency.
Yes, coverage, yes. How would you expect to compare improvements between better temporal coverage versus spatial coverage?
I definitely think from what we have seen over the development of the ICOS network in the Central Western Europe, that with each new station, we got an improved truth recovery rate. Yeah, and therefore I think this is key. It is more important to learn something about a region where you have no observations before than increasing the frequency at stations where you already have observations. So I would always opt for more coverage than for higher temporal frequency.
Thank you. Next question. Gregor, would you like to ask? I think you have maybe you can pick one of them.
Okay, yeah. Sam, first of all, thanks a lot. You already made my day for today. That just is a side note. I had maybe I'm not a specialist, as you know. I had a question on, because you have a seasonal component, this delta, or these fluxes of industrial CO2, and I was wondering what's the background importance of the issue of fractionation during the biological uptake, which is also seasonal. Is that negligible? I mean, I would think that you have a preferential 12C uptake in biological tissue. So is it affecting the baseline, and is it an issue for you?
No, it is actually not due to the construction of the capital delta 14C. So the point is that fractionation during the uptake is happening, but all the C14 data is corrected to a fractionation of -25 per mils. So you can really directly compare them. And the point is the uptake of photosynthesis and also then the autotrophic respiration is basically respiring the actual atmospheric C14 ratio which you had before. Yeah. So this is not really affecting largely the C14 value in the atmosphere compared to the respiration which you have from heterotrophic CO2, because this is biological material which has seen the bomb spike before and which is enriched in CO2 and which we correct for as well. I didn't go into that. Yeah, all of those effects, Gregor, if you're really interested, go to the paper from Fabian Meyer. There we have studied the effect of all of those and also the effect of the nuclear correction and how much it really plays into the uncertainty of our estimates. Maybe Dominic, back to your question before, we correct for the nuclear uncertainty and we take the uncertainty into account of the total uncertainty of our fossil fuel estimates. We're doing so by assuming that it is 100% uncertain, this correction of the nuclear correction. Yeah? And therefore it adds an uncertainty component to all of our observations. Yeah? So it is not neglected, although I decided for this talk to not go into the details of this here, because I wanted to give you the whole picture and not go into the details so much.
Thank you. We have a question from Hannele. She asks, how would you envision utilizing this data in operational systems such as CAMS or the CO2 MVS?
I think we are working towards this. There are now projects hopefully coming up where different European inverse modeling systems will use the data which we produce in ICOS, and they will, on an annual basis, come up with an estimate for this Central Western European region and with fossil fuel estimates. So on an annual basis, you will have a set of 4 different inverse model setups operating with the data which we produce to come up with fossil fuel estimates, also with uncertainties depending on different biases, nuclear contaminations, and so on. And I think that is the first step. Yeah, in the first step, it is used as a validation tool for fossil fuel emissions, and not as a direct component which is integrated in the CAMS system. But in future, I hope that will change. Yeah, in future, I hope also the IFS will become the capability of incorporating radiocarbon estimates directly. And in Corso, they have already started to work on that, but it's not in their operational part yet.
Thank you. So we have next question from Alex. Is the next step also to take into account the regular CO2 observations in the inversions? Or
Yes.
would you like it's better to use the 14CO2 too?
No. As soon as we start to really move away from the Regional Isotope Budget Approach and have the explicit representation of C14 in the model, then we will use the CO2 observations at the same time. This Regional Isotope Budget Approach is the easy case. Yeah, so you can use any CO2 model and just model only the fossil fuel component. This makes it very simple, yeah, and very applicable. But in reality, for sure, we want to go that next step and have both information streams.
We have a related question, at least to the inversion part. So Christoph, would you like to ask? So he asked, do you have an explanation why even with unrealistically high prior uncertainty, your integral and flask-based posteriors differ for 23, and is the inversion overly confident?
You mean that 23 bump which we see?
Yeah, exactly.
Yeah. We looked really into this, and what we are seeing is that in January 23, there are 2 weeks where we see exceptionally high C14 values in the entire domain, not only at one station. Yeah, you see it at Lindenberg, blah, blah, blah. So really all the stations see this anomaly in C14. So therefore, I don't believe it's an observational problem. The flasks see it as well, but the flask then, after these 2 weeks, they have a couple of situations where individual hours have large fossil fuel contamination signal, and that helps the flasks to get that total winter emission right. While the integrated signals, they miss this main winter fossil fuel signal, and then in the fade out of the winter, there is not so much fossil fuel signal left, and therefore this is the reason for this discrepancy. And I have not yet figured out what is actually causing this anomaly in radiocarbon. But this is a hint why the one sample type is more affected from it than the other. Yeah, so it is a real signal. Where it is coming from, we have to investigate further.
Okay, and Emmanuel asks, are you building the samplers from scratch, or is it a company that's producing the?
The samplers only currently exists only in this very nice sketch, which was made by ChatGPT. We are looking for students to actually start working on that. It is part of the John proposal, where we want to investigate, or where we want to build this new type of samplers. We are quite confident that it will work because it builds on really existing technology, which has proven to work for more than 45 years. And it is low tech. Yeah, it is low tech, low price, and therefore I'm very confident that these samplers will be able to make a change for global radiocarbon sampling.
Thank you. That brings us to the end of the questions, but I had a question. I was thinking about the processing time, that, you know, the time it takes for you to process the flask samples and actually get the 14 CO2 data from it. How long this, because this will have an implication when you have increased sampling frequency, now before with Corso and now with the CAMs.
Yeah, typically we always say it's a delay of 6 months. Yeah, between the flask is sampled at the stations and then shipped to us. First of all, you have to have sufficient sampled flask at a station. That is then 1 month until you start shipping the box. Then you ship it to Jena. Then it's a month or 2 at Jena. Then you ship it to Heidelberg, and then we analyze it. So all in all, 6 months is safe. 4 months are maybe possible, but then everything has to be working out perfectly. So that is the typical delay.
Thank you, Sam. We have reached the end of our questions. We've also reached the end of the first ICOS talk. I want to thank you once again for the very nice talk and also for taking the time, and to everybody in the audience who've taken the time to listen in.